I know, he's doing another presentation without a PowerPoint. But honestly, we have to graph inequalities this time, so I have to shade on the insides of graphs, and I couldn't figure out how to do that in PowerPoint anyway. Today, we are talking about graphing and solving quadratic inequalities. We're going to start in two variables, that is with both an x and a y, and the only way to really show a solution set to that is to graph and shade the appropriate region. We're going to do it also with systems, that is two or more quadratic inequalities. Again, you graph them, although with a system you only shade the overlap of the solution sets. Then we're also going to talk about quadratic inequalities in one variable, which we will actually solve. Let's get into it then. An equation with two variables in it would be something like y is less than negative x squared minus 4x. Look at that, I'm really tempted to put that into intercept form or even vertex form in order to graph it. But if you don't remember how to complete the square or factor, that's going to be beyond you. And you can graph it from standard form if you remember the vertex, the axis of symmetry where the vertex is, will be the opposite of b, so positive 4 over 2a, 2 times negative 1, which means negative 2. That's the x value for the vertex. So let me go ahead and draw the axis of symmetry as a dotted line. Now to find the actual vertex on the axis of symmetry, I just take the negative 2 and stick it back in. Negative 2 squared is 4, then I assign the negative, so that's negative 4. Negative 4 times negative 2 is positive 8. So negative 4 and positive 8 makes positive 4, which is up here. As far as an additional point, the y-intercept will be 0, because notice c is missing, it's 0. So if I stick in 0, I get 0 and 0 plus 0, which is down here, and symmetric on the other side. Now, because this is a strict inequality, I have to draw my parabola as a dotted parabola, which honestly I find easier than a solid parabola anyway. I don't know why. I assume it has to do with how the muscles in your wrist move. At any rate, there's the dotted parabola. I just have to figure out whether to shade inside or outside. I can't use 0, 0 to determine which is which because my graph goes right through 0, 0. So I'm going to have to pick a different point. I'm going to pick something out over here, 2, 2. So if I use 2, 2, that says 2 is less than negative 2 squared minus 4 times 2, which is negative 4 minus 8. But 2 is not less than negative 12. So I don't want to shade over here. I need to shade on the inside. Fairly straightforward. When I do two of these at once, the process is not dissimilar, but you have to figure out where they're both shading so that you can find the overlap. Y is greater than x minus 1 squared minus 2. Note that one's in vertex form. And y is less than or equal to negative 2x squared plus 4x plus 2. That's in standard form again. Alright, for the first one, the vertex is at positive 1, negative 2. Sticking in nearby points, if I stick in 0, I get negative 1 squared is 1, minus 2 is negative 1. I'll stick in, I know positive 1, because, or positive 2 I should say, is at negative 1 because it's symmetric. I'm also going to stick in 3 because I'd like to get a little further away. 3 minus 1 is 2, 2 squared is 4, 4 minus 2 is 2, so that's there. Notice this one is a strict inequality again, so I need a dotted parabola, something like this. The other parabola, notice it's going to be upside down because a is negative 2, but the vertex will be at opposite of b, which is negative 4 over 2 times a, which is negative 2. So that's negative 4 over negative 4 is negative 1. Sorry, positive 1. When I stick in 1, I get negative 2 and 4 and 2, which is 2 less than 6, which is 4. The y-intercept will be at negative 2. So using symmetry, I get 2, 2 as well. This one's going to be a solid parabola. So something like this. I can use 0, 0 this time since it's not on either one of my parabolas. That gives me 0 is greater than 0 minus 1 is negative 1 squared minus 2. That's 1 minus 2 is negative 1. 0 is greater than negative 1. So the dotted parabola wants to shade on the inside. Also 0 is less than or equal to 0 plus 2. Also true. So both parabolas want to shade on the inside, and I want just the middle portion here. Not all parabolas will shade on the inside, although shading on the outside is a bit more annoying. There's more area to cover. But you'll be able to do it. So that's solving in two variables, both just the one equation and in a system of equations. Remember to look for the overlap and don't forget dotted parabolas when appropriate. Your book outlines 3 ways to solve an equation in one variable. I don't really like all of those. I will mention briefly that you can solve quadratic equations using a table. If you have a table already, this can be useful, but I wouldn't recommend making a table just for this purpose. I did produce a table for this just to show you what I mean. Note on the table here you can spot the zeros because these ones work out nicely. Here we have positive numbers, there's negative y's in the middle, and positive numbers again on the end. And that's the typical shape for a parabola. So when we want strictly, I wrote this one wrong. If we're looking for numbers that are greater than 0, what we're looking for are the positive numbers. So here, things less than negative 4, and things over here greater than 2. My issue with using the table is that if you have to make the table yourself, or even if it's already produced, if the zeros are not at whole numbers, you won't be able to find the zeros precisely. So knowing how to set your inequalities is a bit tricky. You can get a general idea though. So honestly, a method that will give you the zeros precisely, I much prefer. Your book also recommends graphing as a method, but unless you're using a calculator to graph it and then using it to actually find precisely the x-intercepts, you're going to have the same problem with the table. If they're not nice zeros, the x-intercepts are not nice, you're going to end up doing more work anyway. So what I recommend is their third method, which basically uses a number line. And what we do is we find the zeros ourselves. Oh, I wrote this all wrong. Okay. So to solve this equation, an equation that looks like x squared plus 2x is greater than or equal to 8, first we get it all equal to, greater than or equal to 0. So subtract that 8 over. Now at this point we are going to try to factor. We need two numbers that multiply to negative 8 that add to positive 2, and that would be positive 4 and negative 2. The problem is that x equals negative 4 and x equals positive 2 are not necessarily solutions to our inequality. They're not the only ones. Since this is a loose inequality, those are the points that are going to make it equal to 0. So they're important to note, but they're not all the solutions. They're the boundaries for the solutions. I think your book calls them critical points, which that's not what I'm going to call them. I call them points of interest. So x equals 2 and x equals negative 4. I'm going to start with open circles, and then the first question I'm going to ask is, will those work in my inequality? And in this case they will, because it's a loose inequality. So you want to shade those in first. Those ones work. Now when we did this earlier with linear equations, we only had one point, and it divided our number line into 2 segments. With 2 solutions, we have divided our number line into 3 sections, and each section is either true or false. So there's 3 different sections, and we can check each one by sticking in a number. So 0 is right here in the middle. So if I stick in 0, I get 0 is greater than 8, which is false. This is a false section. And we can check the outside sections. This one here is, say, 3. If I stick in 3, I get 9 and 6, which is 15 is greater than 8. That one's true. So I'm going to shade over here. And the number down here, I could use -5. I could also use -50, since this one goes everywhere. -50 squared is going to be huge, although I guess then I'm going to add to it, it'll be less huge. Either way, it's definitely not going to be, oh good, -50 squared is huge, right. It's going to be definitely bigger than 8. So I'm going to shade over here. You could use -5 or -1,000,000, anything that's in the interval suggested. With quadratics, when we get to next chapter and do polynomials, they'll be less predictable. With quadratics, the outside ones are going to be what you shade, or the inside section. You're not going to have any other combinations. It'll be the outside two or the inside section. So for quadratics, you really only need to check one of them, if you remember, outside or inside. Just to be clear, let's do another one of these. 1/2 x squared plus 3x minus 2 is less than 0. In this case, I could go right into factoring, but I'm not a big fan of fractions, so I'm going to multiply by 2 on both sides. That should make factoring easier. 6x minus 4, 0 times 1/2 is still 0. I multiplied by a positive number, so I don't need to flip the inequality. Now I'm looking for two numbers that multiply to -4 that add to 6, but I'm not going to find them. 2 times 2, 1 times 4. It's not going to work out. So I'm going to go with the quadratic formula in order to find my zeros, my intercepts. So opposite of b plus or minus the square root of b squared minus 4 times a times -c all over 2a. So -6 plus or minus the square root of 36 plus 16. That's -6 plus or minus the square root of 52. 52 is going to be 4 times 13. Yes. -6 plus or minus 2 square roots of 13 over 2, so -3 plus or minus the square root of 13. Well, those are icky numbers. Now the square root of 13, somewhere between 9 and 16, so somewhere between 3 and 4, which means I'm going to have one that's bigger than 0, just barely, and one that is quite a bit less than 0. So this one's -3 plus the square root of 13, and then one over here is going to be -3 minus the square root of 13. You could produce decimal approximations for this if it makes you more comfortable, but 0's in the middle, and if I go back up to the original, -2 is less than 0 is true, so my solutions are going to be on the inside in between these 2 points. Oh, and I need open circles, because this is a strict inequality. So my solutions are -3 minus the square root of 13 is less than x is less than -3 plus the square root of 13. And all of my solutions lie in between there. So to sum up, use factoring or the quadratic formula to find your 2 points, and then figure out whether the solutions to the inequality are on the inside or the outside.